So today is the third lecture of battery fundamentals. Last time we stopped, we covered some of the basics of lead acid battery, and I realized we need to spend a whole lecture on just how the lead acid battery discharges and charges. This applies to all batteries. So one of the topics during lunch today was one electrical engineer mentioned I should call him when we actually start doing lithium-ion batteries. I said it'll be too late. So we're covering some of the electrochemistry basics. And once we cover all these basics, lithium-ion battery will be so easy to understand. But we do need to go through some of this basic stuff in battery technology. I'm using lead acid battery as an example because it's got nice simple chemistry. So today, all we're doing today is explaining this chart. How does the battery discharge? How does it charge? Why do we have this voltage difference? Why is the discharge cell voltage less than during charging? And why is this curve sloping down? Why does voltage decrease as we discharge the battery? Why does the voltage increase as we charge the battery? So this is all we'll cover today. Okay, so let's start. So here's the lead electrode and lead oxide electrode. And I'm going to leave this open right now. So first, let's recap how we get the battery voltage. Well, what are the reactions? So on this lead side, which is, by the way, the negative electrode, and this the positive electrode. So we will not use terms like anode and cathode, because when it comes to batteries, there's no such thing as an anode or a cathode, because they switch. During charging, during discharging, this would be anode. During charging, this will be cathode. So they flip. So it's better to use the term negative, positive. Also, if you look in your batteries, there's always a positive terminal and a negative terminal. So those terminals don't change, but the anodic and cathodic reactions change. So let's see. So we have an open circuit. So we have this VOC, the open circuit voltage. Where does that come from? So on this side, we have a reaction. The sulfate ions will diffuse to the lead. Diffusion means motion under the influence of concentration gradient. So these sulfate ions will move around under the influence of concentration gradient, and they'll react with lead. So lead atom plus SO4 minus 2 will give you the lead sulfate. But this side has two negatives, so I need to put 2 electrons on that side. So notice that as the reaction proceeds, you create more electrons. So the lead becomes negatively charged because of this reaction, the sulfate ions combining with lead giving you electrons. So this becomes negative. It keeps becoming negative until, so let's say if this becomes very negative, then the sulfate ions cannot, the electric field will push them away, right? Because this is negative and this is negative. So this reaction reaches equilibrium. At some point. So at that point, there's a potential between the liquid and the metal. So we normally say, well, we say this is plus, this is minus. So this potential, what should I call it? So if we measure this potential, it'll be minus 0.356 volts under standard conditions, meaning room temperature and standard concentration of sulfate, etc. Now, let me just digress a little bit. How do you measure this potential between the liquid and the metal? So if I have a metal, let's redraw over here, lead in a liquid, I want to measure this potential. So you need to put a device over here to measure, like a piece of wire or something. So what we do for that is we use what we call standard hydrogen electrode. So essentially what we do is we bubble hydrogen gas, and our actual piece of metal is platinum. So platinum is inert. So you bubble hydrogen gas, and so you measure this voltage between the platinum and the lead, and the reaction on this side will be H plus electron giving you H2 gas, and this is also under equilibrium condition, so under standard state, meaning this constant activity is 1, so concentration of hydrogen ions is 1. We are at room temperature 298 Kelvin, etc. So we use this as a reference electrode. So we call it standard hydrogen electrode. So we cannot measure the voltage between the metal and the liquid. We can measure the voltage between the metal and a reference electrode. But what about the voltage between here and here? So we want to measure this voltage. We can't do it, so we measure the voltage from the platinum to the metal. But there's a voltage over here, right? If this voltage was 0, then we're home free, right? If this voltage is 0 and we're measuring the total, then we know this one. But this voltage is not 0, but we assume it to be 0. So we say that the E0 for H plus H2 gas, this voltage is 0. That's the assumption we make. We assume it. The word assume is missing over here. So that's how we measure the potential between the metal and the liquid. So any questions at this point? No? No questions? Okay. Okay. So now we're done with that. And it turns out that this voltage, yeah, we know it's not this voltage, but between this and a standard hydrogen cell is minus 0.356 volts under standard conditions. And this reaction goes back and forth, and it has a rate to it. In other words, we are going in that direction, coming back in this direction. It turns out there's a reaction rate. And that reaction rate is called exchange current. So there is an exchange current. I'll explain this in a few minutes. But in terms of amperes, we know how many amperes are going this way and this way. They're both equal, they cancel each other. But there is exchange current that can actually be measured. Okay, so at this point, let me rub this side. And so let me draw the diagram that has, which is fundamental to our class today. I'm going to plot voltage versus log of some current. So here, this voltage is minus 0.356, right? So let me write down over here, minus 0.356 volts. And we mentioned there's an exchange current going back and forth. So let's say this is our I naught, the exchange current. So we have a spot over here. So this spot on this diagram describes the electrochemistry of this electrode. Okay, so we're done with this electrode for the time being. We are in open circuit condition. Now let's go to this one. So this electrode, I think I'm going to write in red. This one has a reaction which would be, so I'll write over here. So SO4 minus 2. So this SO4 will also go in this direction and attack the lead oxide. So it'll react with the lead oxide, and these hydrogen ions will also go in that direction, and 4 of them will, and 2 electrons will give you PbSO4 plus 2 water. So we have lead oxide is reacting with the sulfate and hydrogen ions, giving you lead sulfate. The same thing happened over here. So both these get covered with lead sulfate. So let me draw in blue. So right now we're open circuit, and yet both these are getting little coverage of lead sulfate. Probably not much, because in the process of this forming lead sulfate, it becomes negatively charged. And on this side, notice the electrons are being consumed. So this gets positively charged. So as this, okay, so the voltage is from here to there. So when this gets positively charged, the hydrogen ions cannot, they get repelled by the positive charge. So this reaction too comes to a equilibrium condition such that both these reactions going forward and backward are the same. And this has an exchange current too. So let's draw that. So, also there's a voltage over here, which is plus 1.685 volts. So let me write down plus 685, and this has a exchange current too. So we have this dot over here. So we're an open circuit, and we have this 1.685 volts. This is under standard conditions. What that means is that the sulfuric acid concentration would be 1 molarity. Even though we know that in a battery, sulfuric acid has 6 molarity, right? But these voltages are under standard conditions. Or, okay, maybe I'm wrong. Maybe it's 6 molarity gives you that. Anyway, so these are the voltages under standard conditions. So now notice that this voltage over here, if you look at the difference, this is the sum of the two, right? So this is about 2.04 volts. So that's what this would be over here, 2.04 volts. This side is positive, and that side is negative. So this is a recap from last time. So we just, now we understand what happens under open circuit conditions, right? Okay, so what do we do next? We want to study how so right now we are over here. So this is this condition over here, open circuit, right? So now we put a resistor, a load across this terminal. So we put a resistor. Load would be resistive or whatever. So R load. So when we put the load, these electrons, so this side is negative, this side is positive. So electrons will flow in this direction, and current, which is a negative of electrons, will flow in that direction, right? So now we're studying discharge. So what happens is we get an effect that this 3.356 volts was under open circuit conditions. But when we remove electrons from this electrode, that point will move, right? Because we're removing electrons, this point will move upwards. So we're making this, so because we're removing electrons from here, this is becoming positive. Plus there'll be current, there's current flowing. See, before there was no current flow. So there'll be current flowing. So two things happen. We are removing electrons, so this is becoming positive. So the dot is going up, and we have current flow. So the current is increasing. So the net is this curve goes in this direction. So when we put a resistor over here, this current in this leg, actually electrons going that direction, current in that direction, this current will increase, right? And the voltage will also increase, the voltage of this, because we're removing electrons. So what is the slope of this current? What's the beta? So the slope is, so there are two things. So the dot is moving this direction and up. So what is this voltage? So we moved from equilibrium. So we call this, what's that, eta, and this is anode, and it's negative. So let me call that. So this eta anode is negative will be equal to beta AI log I over I naught AI. So basically what we're saying over here is that this upward motion of this point depends on this current. So the current right now over here will be this current I. So we take this current I, divide that by I naught. So this is the I naught AI. And take the log of this difference, and that results in this height. In other words, this is the slope of this line. So to recap, when we connect a resistor, electrons will flow in this direction. So electron current increases. We're going that direction. Because we're removing electrons, the voltage is increasing, so voltage is going up. So this is called Tafel curve. So Tafel came up with this idea. And what we will do is, we will derive this soon, one of these days, but for the moment, let's assume it. Okay, now the same thing happens over here for the lead oxide. So just to remind ourselves, the red is lead oxide electrode, and this black line is lead electrode. So on the lead oxide, what we're doing is we're pumping electrons this way. We're removing current, pumping electrons. So the voltage will decrease. So this point will move down, and we are increasing current. So current is increasing. So current is going that direction. The net result is this curve goes like this. So this curve also has slope of, we'll call it beta. It's cathodic and it's positive. And if I were to draw a line over here. This will be N eta C plus. So this eta C plus will be beta C plus log I over I naught C plus. So just to recap, the lead oxide, we're adding electrons to it, so the voltage is coming down by this amount eta, and of course the current is going up. But these two currents are equal, right? The electrons coming from the lead, they're going to lead oxide. So that's why I drew this vertical line. So now we're dealing with this current I, which is the same current entering the lead and leaving the lead oxide. And the circuit is completed through the electrolyte. And there's a resistive element over here, which we will call, let's call it Re for electrolyte. So the electrons flow here, ions flow here, and round we go. So this, everything I described over here is called activation polarization. So what I've described right now is called activation polarization. And this is one of the most difficult concepts to understand in electrochemistry, this idea of activation polarization. So if you're a little lost, it's understandable. So what activation polarization is, these voltages change because of current flow. So how much change do we have? That's the change. So this is voltage. So these are the voltage deviations. So on the lead, this was the open circuit voltage, and because of current flow, the voltage has changed across that electrode. Same thing with the lead oxide. This was the equilibrium condition open circuit voltage, but because of current flow, the voltage across the electrode changed. And the books on electrochemistry don't go into these details that I'm going through right now. So this is activation polarization. Also notice that in both these reactions, the sulfate ion is being consumed. So sulfate ions near the surface are being consumed here and also on the lead electrode. So this gives you a concentration gradient, right? So there'll be, I can think of, there'll be a region around this thing where the sulfate ions are depleted, right? Because they combined in this reaction. So similarly over here, there'll be a region where the sulfate ions are depleted. So there's a decrease in sulfate concentration, and that also affects this curve. Now, last time we did some of that, so let me do that. So what is this voltage when we move away from our standard conditions? So here's a reaction. So what happens is, because of concentration, because of sulfate ion concentration depletion, this voltage also changes. So the new voltage E is equal to E naught, and I'll call this A minus for this is now an anode, and it's negative, plus RT over 2F log of reactants over product. So the reactants, the only reactant to consider is sulfate ion, because these other, like lead and lead sulfate, the activity we can consider to be 1. So the only active species here is sulfate. So this is the equation. So what this tells us is that this voltage is equal to this voltage when this is equal to 1, right? Log of 1 is 0. But if this moves away from 1, then you have a change in this voltage. So this voltage also depends on the sulfate ion concentration. So the voltage across the lead electrode depends on the sulfate ion concentration. So, okay, I made a mistake over here, and this should be to the -1. The reason is, let me move over in this space over here. So let me just slow down over here a little bit. I think I've taken some big steps. Suppose I have A plus B giving you C plus D. Now this is just a chemical reaction, but in electrochemistry, we also have electrons involved in the reaction. So suppose you have a reaction with these products, A, B, C, D, and the electrons involved. So notice I put the electrons on the left side, because when it comes to measuring or dealing with potential of electrodes, so what's the potential across electrode? We deal with reduction reactions. So this is a reduction reaction because it deals with consumption of electrons. So any reaction where electrons are being consumed is a reduction reaction. So you might say, oh my God, this is all chemistry. But I promise you, most PhDs in chemistry don't know this stuff, you know. So they've had one lecture on it, just like you. So you have a reaction like this. When the electrons are being consumed, it's a reduction reaction. So now, what is the potential across this electrode? And the potential will be E is equal to E naught plus RT over NF log of reactance concentration of A times concentration of B over concentration of C times concentration of D. So this is, and we haven't proven this, so we're just assuming this, right? So the electrode potential will depend on the potential under standard conditions. So this would be, and to you it's obvious what this is. When the reactants and products all have activity equal to 1, then this goes away and we're left with this is like the under standard conditions. This N is the number of electrons in this reaction. For us, in a lead acid, N is always equal to 2. So this is what I used to come up with this equation. And in this equation, I should have said the reaction is this direction. So these are the reactants and these are the products. And notice products go on the bottom. That's where the sulfate ion concentration goes on the bottom. So now notice over here that when the sulfate ion concentration decreases, this value goes up, right? So at this point, in this region surrounding the lead electrode, when the sulfate ion concentration decreases, this value goes up, so that value goes up. So now look over here. So we are at this point because of activation polarization. So because of current flowing, we have this change in potential. But now notice, because sulfate ion concentration is decreasing, so we get another increase in that electrode potential. So this point goes up over here. So this curve let me draw in black. So let me make this dotted. So this is the activation, this was the activation polarization. Because of concentration polarization, this curve takes an upward move. So this little jog over here, this is because of concentration polarization. That's an R. And this one, so that's a little jog over, that's a little increase. This one is activation polarization. So we have two polarizations. So the activation polarization is because of current flowing across the electrode, and the concentration polarization is because the change in the sulfate ion concentration around the electrode. So the curve takes an upward slant. So I've covered a lot of material. I know this is complicated. So now, what about the lead oxide? The same thing happens on the lead oxide side. We lose sulfate ion concentration surrounding this electrode, right? And for lead oxide, I can write this equation as E PbO2 is equal to E0 for equilibrium, C for cathodic reaction. It has a positive, it's a positive electrode, plus RT over 2F. Now I'll use this reaction, the one in red. Actually, I should write this in red. So this is log of, so this is written in the reduction form because the consumption of electrons. So these are the reactants, and they go on the top. So I can say SO4 minus 2 H plus to the 4, and I'm ignoring lead oxide, lead sulfate, and water. I'm ignoring those, but those have activity of 1. So notice now, as the sulfate ion concentration decreases around the lead oxide electrode, this value goes down, right? And also the hydrogen ion concentration decreases. So the potential across the lead oxide electrode decreases. So the potential goes down from here to there. So this curve takes this form. So this portion is concentration polarization, and this one is activation polarization. So just like we have concentration polarization on the lead electrode, we have the same polarization on the lead oxide electrode. So why is this important? So what is the cell voltage now? What is this voltage? So this voltage, so let's write that somewhere. If I can move to the board to the right. So under these, so we are discussing right now discharge of the cell. So what is the cell voltage? So now we apply the Kirchhoff's voltage loop. So we have V cell, and this side is positive, this side is negative. So I come this way, and I go from positive to negative. So I'm going down. So I write down minus 1.685, that's this value, and minus this. So minus, I'll just call it NC. So I'll add up these two. So I'll call the whole thing eta C. So I started off with this voltage. I'm coming down this way. So I step down from plus to minus. So that's why I have a negative sign. And the voltage across this electrode is 1.685 minus NC, NC being this value, right? And then I go from here to there. I go from negative to positive, so I have to add, but except I'm adding a negative term. And so to this negative term, I add an A. Oh, I forgot. In between, we have IR. So in between over here, I shall written minus R, I times R electrolyte. So this should be equal to 0, right? So when you, in Kirchhoff's voltage loop, when you go around the loop, you end up with 0, right? So which Maxwell equation is that? So all of electrical engineering is based on 4 Maxwell's equations. So Kirchhoff's voltage loop is based on one of those 4. I have to think about which one it is. Okay, so which one is it? Okay, so when the professor doesn't have the answer, he gives it as a homework problem. Okay, so we're not selling anything, but the voltage across the cell is 1.685 minus NC minus 0. Actually, what did I do over here? So this should be, oh, I got it wrong over here. So this was plus minus, this was plus minus. So oh, okay, that's okay. So this would be, so this should be plus 356 minus Na minus R electrolyte. So this is the voltage across the cell. So when you have your load will be measuring this voltage. So notice that the cell voltage depends on the current. So the current increases. If the current increases, the cell voltage will, this voltage go down. That's the reason why I'm plotting this at constant current. So we have to be careful that these curves we have to plot at constant current. So this plot is independent of current. And also this NC and Na, these polarization terms are also a function of current, right? As we increase the current, these values go up. So that's the discharge case. So let's talk about the charging case. What happens? Okay, let's stay with the discharge. So what happens is with time, as we discharge, so let me write down over here what actually happens during discharge. So during discharge, the SO4 minus 2 concentration decreases, right? So that's one reason the V cell goes down, right? Because of this. No, the V cell should go up, right? For this one goes up, this one goes down, but the difference decreases. So second is lead sulfate forms So this is non-conductive. Therefore, V cell also decreases because this resistance value will, you can add that to the electrolyte. So we have our electrolyte, you can add the resistance of the lead sulfate to that. So this also causes a decrease in the cell voltage. So that's why during discharge, the voltage keeps decreasing. So is there anything I forgot? I think this probably covers it, right? During discharge, that's what happens. So now during charging, why do we have higher voltage? Why do you have this shape of the curve? So let's do charging now. So during charging, okay, so let's talk about charging. So during charging, the reactions reverse. So we have PbSO4 plus 2 electrons giving you Pb plus SO4 minus 2. That's the reaction on the lead electrode. So this is on the lead electrode. So let's stay with this for a moment. So now notice the SO4 minus 2 concentration is increasing. But before that, okay, so since we're dealing with charging, let me change this to charging source. So here's a source. So this is a V cell. But now we are applying a voltage. So instead of small v, let me make it capital V, which means I'm applying like a DC voltage over here. I'm charging. Actually, it's still small, but this voltage might change because you're dealing with constant current. So we apply a certain voltage. Now the current is flowing in this direction. The electrons are flowing in that direction. So let's stay with the lead electrode. So notice we're pumping electrons into the lead electrode. So which means the lead electrode is getting negatively charged, right? So this point will go down now during charging, but also we are applying current. So current is increasing and the electrode is becoming negative. So we get this plot, and this also has a slope to it. So during discharging, the potential across the lead will go like this. Now what about, so this is our activation polarization. But what about concentration polarization? So when we are charging the cell, the sulfate concentration increases, which means that if the sulfate concentration increases, this value decreases. So this curve will go down like this, and this difference is a concentration polarization because the sulfate concentration decreases. Now, okay, so that takes care of the lead electrode. What about the lead oxide electrode? So this one, the reaction is you have P, let's say, so we're going in the opposite direction. So we have Pb SO4, which is the surface of this lead oxide, plus 2H2O gives you 4H plus SO4 minus 2 plus, let's see, what else? Plus 2 electrons. And I'm missing one thing over here, plus PbO2. So what is happening during charging is lead sulfate is combining with water to give you hydrogen ions, sulfate ions, electrons, and lead oxide. So lead oxide is being produced and lead sulfate is being reduced, right? And this, so what about the potential in this case? So the potential E across electrode, okay, before you go there, getting back slowly to this page. So we are pumping positive charge into the lead oxide. So the voltage is going up. So voltage will go up, and we're pumping current. So current increases. So this curve will go up like this with a certain slope. So that's the activation polarization. So in terms of the concentration polarization, so sulfate ion is decreasing. It's increasing. Sulfate ion is increasing. Therefore, the voltage across the lead oxide will increase because sulfate ions are increasing. So the concentration polarization will raise this curve. So maybe I should just draw in blue for charging. So the net result is this curve will be like this for the lead oxide electrode. For the lead electrode will be like this. So now notice the voltage across these two is this much. So notice the voltage is increased. So now during charging, let's write down the cell voltage. So same. So this time the V cell will be 1.685 plus NC plus 0.356 plus Na minus R electrolyte. So notice before we are subtracting the concentration polarization and activation polarization, now during charging we're adding it. So the voltage of the cell during charging is more than during discharging. So that explains why we have this increase in the voltage. So now, why does the curve go up? So the curve goes up because as we go up this slope, the sulfate ion concentration increases. So that is increasing the voltage, plus the PbSO4 is dissolving. So this is the resistive element. So you're removing a resistor from the circuit. So instead of the voltage dropping across this lead sulfate resistive element, is dropping across the V. So basically you remove a resistive element in series with this charging source. So by the time you get over here, you mostly have lead oxide, almost no lead sulfate. So this is also mostly lead oxide. And at this point, you have lead sulfate, which is covering both electrodes. So during discharging, the lead oxide and the lead, they get covered by lead sulfate. So you end up with lead sulfate on both the electrodes. So the decrease in voltage is because of SO4 minus 2 decreasing, and also the lead sulfate forming, which is resistive. And during the charging operation, the lead sulfate dissolves away. You end up with lead oxide on the lead oxide electrode and just lead on the lead. So there is no lead sulfate over there. So in other words, as you're going that direction, you have more lead sulfate, which is resistive, voltage drop across that. As you go to the left, there's not much lead sulfate for that voltage drop. So this material I covered, it's a huge amount. So if some of you are lost, I can completely understand. But if you have any questions, let me know. We can discuss any details. So on that note, I'll call it lecture number 3. So next lecture will be 2 weeks from now, but because next week we'll do physical metallurgy. So next week will be phase diagrams, and the week after, I think I'll have a lecture on thermodynamics of cells. In other words, we have used these where do these reactions come from? So I'll go into that now. So thanks for attending. No questions?
So maybe just one little minor question.
Sure.
So the standard cell that I have here, 2.04 volts, it's a little bit below, say, typical wet cell lead acid battery voltage.
Yeah, right.
2.25 volts, or some VRLAs are 2.1 volt.
Yeah.
We're just wondering if knew what some of the differences
Right.
were from standard in some of those.
Right. So by the way,
Data center applications.
so your car has 6 cells. So in series, that's what gives it 12 volts. But to your question, so this 2.04, that's the cell voltage under standard conditions. Except I think when I say standard condition, I should say 1 molality for the sulfuric acid, but it's 6. So the voltage will change depending on the concentration of the sulfuric acid. And we measure the concentration of sulfuric acid by measuring a specific gravity. So when specific gravity increases, we know its concentration is higher, right? So people, they'll put this bulb in the electrolyte, see how much it floats, so you know what its specific gravity is. From that, you know the concentration. Yeah. So today's lecture, one of the problems is you won't find this in a textbook. So this curve I got was from a paper that's published. So they said, this is the actual curve under constant current, but they didn't tell me what the constant current is. And they don't have to, because the current will depend on the size of the battery, right? So you can have a tiny battery and a big battery. They can behave the same way, but the current will be different. So, but the paper did not describe the details I'm describing over here. So this took me some time to pull all this information together. Yeah. So the electrochemistry books, they do a very poor job on explaining the details. So next time what we'll do is, we'll try to do 2 things. We'll try to explain where this equation comes from. So this is called the Tafel equation. And we'll explain where this equation comes from. So to me, I mean, these things they're good to know. So, because if you're making if you're Newton and you want to make big discoveries, you have to know the fundamentals, right? So there's another question I ask myself. Do I really understand the material? How do I know I understand the material? What's my test, right? So my test would be, if I go back to 1700, when Newton was alive, he was alive in 1700. So let's suppose I happen to wander through Cambridge and Newton sees that strange looking guy wearing weird clothes. He said, where the hell are you from, you know? So, oh, I'm from 2017 from Poughkeepsie. He says, what Poughkeepsie? You know, he'd never heard of Poughkeepsie. But then he starts talking and he says, oh, can you explain to me what is a voltage? What is an ampere? What is an ohm? What is a potential? So I should be able to explain to him what a volt is, right? So we did that in the first lecture, right? Probably we all forgot what a volt is, right? So the volt is the amount of work done to move a unit charge from here to there. If the voltage difference between my 2 points here is 1 volt, and if I have to move 1 coulomb from here to there, the work done is 1 joule. But then, of course, I get into trouble. He'll ask me, what is a joule? You know, it goes on and on. So that to me is understanding a subject. And I never thought about it like this until recently. And so let me leave you with one question. Take a blank piece of paper like this and write down on this paper log of x, and explain to yourself, what is log of x? Where does it come from? And along your inquiry, you'll come across a term called E. Now, E is not any number. E is a very special number. Some people say, oh, no. We have log to the 10, we can have log to the E. No. Log to the 10 is special. So log to the base 10 is special. So is log to the base E. So the question to you is, where does E come from? So the thing to do is to take a blank piece of paper and not look at any textbook and try to derive the value of E. E is a very special term. Now you could cheat. Like we know what's the differential of log x, right? So whatever information is in your head you can use, you know, like differential of, so let me give you a hint. What is 1 over x dx integral? It's log x, right? So there's a hint, you know, yeah. And from here, you can get to E. So my point on all this is, I personally believe in fundamental understanding of a subject. So that's why next time we'll do the first law of thermodynamics and the second law of thermodynamics. Now I'm told there's a third law of thermodynamics, which I haven't figured out. But I think 2 laws is enough, you know. Okay, guys, let's call it a day. Thanks.